In section 5.3, we're going to talk about the binomial probability distribution. The binomial probability distribution is one of the well-known discrete probability distributions. Before we actually discuss the formula or the function form of the binomial probability distribution, however, let's talk about the binomial experiment. Now, the word binomial, the prefix bi meaning two, and nomial means terms. So binomial means two terms. And in context of what we're doing here, that means two outcomes for us. So here are the signature of what would be a binomial experiment. First, we got to have n trials. Remember, a trial is a repetition of an experiment. So n trials means you repeat the experiment n times. These trials must be identical and independent. Identical means that they are conducted in exactly the same way, using the same instruments if an instrument is used. And independent meaning there's no correlation between the outcomes. So the probability that any outcome will be observed is independent of other outcomes. So we're talking about statistical independence here. Now, how we can actually ensure independence in an experiment is by virtue of how the experiment is conducted. Okay. Each trial is Bernoulli. That means there's only two possible outcomes. It's kind of a 0 or 1 effect. We can generically define these two possible outcomes as success or failures. Now we got to be careful here when we talk about success and failure. Success and failure may not have their usual connotation. Usually in everyday life, success is a positive thing and failure is a negative thing. But in context of what we do, success could be a very negative thing also. So for example, in a group of size, let's say 10,000 people, success would be if I find people that are suffering from acute prostate cancer. Or it could be any sort of other ailment, something negative. It could be, for example, a success is that if we find a defective part, an electronic part that is defective and not working. So it's however we define success in context of the experiment. A failure could be a good thing also. For example, a failure is in a childbirth. A failure is to observe a boy. Okay, in that case, it doesn't mean the boy, that childbirth necessarily, the child will be a failure. And the probability of success we assume is fixed, and we call that little p. And the presumption is that it remains constant or fixed as we go from trial to trial. Now, how can we justify this probability of success being fixed? Is that our sampling has to be done with a replacement. So we take a member of the population out, whatever the probability of selection of that member is. By putting the member back into the population, that same probability will remain. So it's not going to be changed. If the sampling is done without replacement, that probability will change, especially if the population size is small. But again, our assumption is that the population is large and the ratio of sample to population is less than 5%. So for example, if I have a population of size 1,000, 5% of 1,000 is going to be 50. So our sample size is going to be 50. And in that case, we can actually assume the probability of success is fixed, even though we sample without replacement. Okay. And as long as sample size is less than or equal to that, so 49, 48, 40, 30, so on would be good. Okay. So when all of those are in place, then the binomial probability distribution is given by this formula. Now the formula, the components of this formula, parts of it we actually have observed, we have seen portion of this formula. The upfront stuff what you have in front is the nx notation, right? We have seen that in latter part of chapter 4 when we talked about counting techniques. So let's just kind of remind you here what this n choose x notation means in parentheses. So the nx here, in this case, nx means n factorial divided by x factorial, and then n minus x factorial. We refer to this as combinations, right, in chapter 4, and that's what it is in here. And this formula, by the way, we could derive the formula for you. Maybe we can do that later on, but we're not responsible for derivation of the formula. But the way this works is that a sequence of success and failures, let's say I have, there you go, 4 items here, and I want to have 2 successes in a sequence of 4. Well, I could get success on the first, second, and followed by 2 failures. Or I could have success, failure, success, failure in that order. Now there's so many of these sequences, right? Well, the quantity that's in front of this formula, the nx, counts how many of these sequences of success failures are possible. That's what the nx does. Now, if I think in terms of probability of a particular sequence here, probability of S, F, F, due to the assumption of independence that we have made up here, right? We said the observations, the trials are independent. So because of that, then we can write this, and let me erase this lower sequence here. I can actually write probability of that sequence as probability of S times probability of S times probability of F times probability of F. And if you let probability of success be P, that means probability of failure is going to be 1 minus P, right? Because remember, these are Bernoulli trials. So probability of success, that's probability of success up here, we defined it to be P, little p. Okay, so that means probability of failure would be 1 minus that. So success is P times 1 minus P times 1 minus P. So that particular sequence has probability of P squared times 1 minus P squared of happening. And that is indeed what the latter portion of this formula is derived from. That's how we get that latter part of the formula. It's something in the nature of what I'm doing. Now, again, any one of those sequences, so I could have, this is one way the sequence of success failures could occur, where I have 2 success, 2 failures. Another way could be I have success followed by failure, failure, success. That sequence also has probability P squared 1 minus P squared of happening. Okay, and so does the next sequence. If it's F, F, S, S, that also has P squared 1 minus P squared. So notice all of these sequences, each of them has that same probability of happening. So a sequence of success failures, in my example, I have 2 successes. A sequence of 2 successes and 2 failures could occur this way. It could happen this way, or other ways. Well, how many ways are there possible? It turns out that there are. I have 4, and I want to have 2 successes. So 4 choose 2. This is how many sequences of success and failures there are. Okay, and that's going to be 4 times 3, 2, 1, divided by 2, 1 by 2, 1. And the answer is 6. So there are 6 sequences possible. And that's what this upfront stuff does. Okay, the nx notation does. Now, because each of these sequences, each of them has the same probability of occurring, that's why we end up multiplying by 6. Because otherwise, I would have to add the probability, this probability plus this one plus 3 more like it, And because every one of them are the same, and I have repeated addition of the same expression, so I can write it as multiplication. So the answer is to probability of 2 success in this case. Probability of 2 successes is going to be 6 times p squared 1 minus p squared. Okay, so that's just for my made-up example on the margin. Just want to try to clarify this formula a little bit for you. Now, x here is the number of successes. So in fact, let me read this for you. So in a binomial experiment, we're going to let x be the number of successes in n trials, with probability of success being p. Then the probability distribution of number of successes is given by this formula. The number of successes could be 0, means no success, 1 or 2 or 3 or 4, all the way up to potentially all n trials being a success. And that's what this is. Okay. Now, for a binomial probability distribution, we're interested in finding individual probabilities, and we're going to be doing that in StatCrunch, and in fact we're going to look at the shape of the distribution also in a few moments. And we're interested in a couple of other statistics, namely the mean and standard deviations. So the mean is found this way and the standard deviation is found this way. Now remember, binomial is a discrete probability distribution, so we could have also written mu as sigma x px, like we did earlier in previous section. And sigma squared, remember the variance is x minus mu squared times px. We can still do those, but we don't want to. For binomial, it's a heck of a lot. It's a lot easier to simply use these closed form of the formulas to do that. Okay, and indeed we'll do that later. Now, here what we're going to talk about the sampling and binomial distribution. Remember, in order to have a fixed probability of success from trial to trial, it does require that the sampling is done with replacement. Okay. Otherwise, if it's not, that probability actually will change. So then we get into a whole different probability distribution. If that is not the case, in fact, the sampling will be what we call a hypergeometric distribution. Okay, and we don't cover hypergeometric distribution in this course, but that's what it ends up being. So it's a whole different animal. And what I said earlier was also this: if the ratio of sample to the population size is less than or equal 5%, then we can actually assume the the probability of success is fixed and remains fixed from trial to trial. That's just a simplifying assumption. It's not really true, but it's not like something that's going to make or break our problems or the answers. So let's take a look at this example. In this example, we have traffic fatalities and intoxication. Okay, so the question reads: the National Council publishes information about automobile accidents in Accident Facts. According to that document, the probability is 0.4 that a traffic fatality will involve an intoxicated or alcohol-impaired driver or non-occupant. So there you go. This is your success. We're talking about a traffic fatality. That's not a good thing. That involves intoxicated or alcohol-impaired occupant. That's the condition that we defined. That's X. Okay, that's the random variable X. So probability of success here, probability of success, let me just call that little p as your formula does. A little p here is 40%, pretty high probability at that. In 8 traffic fatalities, now these are the number of trials, 8, so n is 8. Find the probability, the number y, that involve an intoxicated or alcohol impaired driver or non-occupant is. So again, notice this is what your random variable is. Okay. We want to know what is the probability of that event, y, is exactly 3. I'll do this, actually I'll show you details of the computation of this one, and then beyond that we're going to go to StatCrunch and use the StatCrunch to do this. Probability of exactly 3, probability of at least 3. Now remember, at least 3 means 3 or more, right? That's probability that x is 3 or 4 or 5 or 6 or 7 or 8. All 8 qualify. And we can write this as an inequality greater or equal to 3. Okay, and finally for part A, probability of at most 3. Remember the semantics of probability. At most 3 means no more than 3. At most 3 means 3 or fewer. Okay, so we can do part A in just a moment here. Now, the other thing is, for any binomial probability distribution, we need n and p. So n and p are called, let me actually go back up and write this over the formula. We call these n and p the parameters of the distribution. You see that right up here? I overlooked it there. The parameters of the binomial distributions are np. So what do we mean by that, the parameters? That means in order for us to be able to identify and find probabilities of events for a binomial probability distribution, we need to know the number of trials and we need to know the probability of success. And here's how we're going to write this probability. We're going to call this B N P. That's how we identify our binomial probability distribution. Okay. So, having said that, then in this exercise, we have a binomial probability with n8 and p is 0.4. Those clearly identify what kind, because there's not a single binomial distribution. Depending on n and p, we get countless number of binomial distributions. Now, let's actually find this part A, and then we will do the latter part of this in StatCrunch. Okay. So for probability of y equals 3, so I'm going to use the formula we had. The formula is going to be 8 choose 3. P is 0.4 cubed times 1 minus 0.4 to 8 minus 3 power. Okay, so that's going to be, now 8 choose 3, that's 8 factorial. And then 3 factorial, 5 factorial. 0.4 cubed turns out to be 0.064. Okay. And 1 minus 0.4 is 0.6. 0.6 to the 5th power, that's 8 minus 3. That's what that is, 5. So that number is going to be 0.07776. Again, that is 0.6 to the 5th power. Okay, that's what this number turned out to be. Now the factorial part, you can do that one as 8, 7, 6, 5, 4, 3, 2, 1. I stopped at 5 factorial because I see one down here. But I'm going to write out 3 factorial. The 5 factorials are common factors. They cross out. 3 by 2 and 6, those are common factors. And 56 is the upfront number. So what that means is this. There are 56 ways. 56 ways I can get 3 successes in 8 trials. 56 ways. So I can get success, 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 and all of the remaining ones would be failure. There you go. And probability of that particular sequence is what this number is. that probability is going to be 0.4 cubed. Notice I have 1, 2, 3 successes, and by virtue of independence we multiply those, you get 0.4 cubed times failures are 0.6, and we got 1, 2, 3, 4, 5 of them, so it's like 0.6, 0.6, 0.6, 0.6, 0.6, like that, 0.6 to the fifth. So a very specific sequence of success failures in this case has this probability, and 56 is how many of them there are. Now if you do the math here, plug in 56 for the fraction times 0.64 times 0.07776, and the number I got, and we will verify this number later on in StatCrunch, I got 2787 for that number. Okay, and there you have it. That's probability of exactly 3 successes. Note how long it takes to do a single probability for exact value. Imagine now, let's say if you want to do this part and this part. If you want to do this by hand using the formula, I actually have to do this formula that we just did 1, 2, 3, 4, 5, 6 times for the second part. And of course part of it is done, the probability of 3, we have that done here. Oh, and the other thing I just noted, because the author he used y, so let me adjust my x to y. It's not a big deal, it's just to be consistent all the way through. So all the x's in this exercise are y, but that's not a grave mistake. All right, and I'm good with this one. So let's go to StatCrunch and try to do this whole exercise, as much of it as we can, parts A and B, and we'll come back to parts C and D. Okay, C and D we do by hand, but parts A and B we're going to do in StatCrunch. So remember, part A, we want to find those probability in part B between 2 and 4 inclusive. Between 2 and 4 inclusive. Okay, so let's go to StatCrunch. Okay, so I'm actually in StatCrunch now and showing you. Remember, how to get to StatCrunch is through my MATLAB. And I want to show you this probability. So we're going to go to, first of all, in order to do this, I'm going to go to Stat, and then we're going to go to Calculators, Stat, Calculator. Now here we have a good list of well-known probability distributions. So the one we're working with is actually the binomial, right? So I'm going to click on the binomial. So remember, we went to, let me show you once again. You go to Stat, Calculators, and you go to Binomial. Now this is just the default that pops up. Notice it gives you the probability distribution. The default is N, P, 10, and 0.5. We don't need those. We're going to actually put in our own numbers in here, right? Remember, for our exercise, N was 8 and P was 0.4. So I'm just going to punch in 8 and change that to 0.4. Now down here, let's do part A at the same time. StatCrunch calls the variable x, your book called it y, no problem. We want to find probability of exactly 3, right? Compute, and there you have it. Notice again that bar, the highest bar is 3, that is in color, in red color. So what you're looking at is actually the probability distribution. You see that? That is the probability distribution for this variable. And so probability of exactly 3, we found it to be 2787, and there you go. See, that's confirmed, 2737. So that's for part A. In part B, we wanted probability of at least 3, so you're going to change that to greater than or equal to. Just left click once, go to appropriate inequality, greater than or equal to 3, and again what StatCrunch does, it actually highlights these bars that qualify for that statement. So now 3, 4, 5, those outcomes, their probabilities are in color. that answer is going to be 6846. 6846. And usually probabilities we round to the nearest 10,000ths. Now, probability of at most 3 means less than or equal to 3. That probability is going to be 0.5941. I will transfer these to my notebook in a few moments. And there you have it. So it's pretty easy, isn't it? Well, one of the questions also in part B is said probability between 2 and 4 inclusive. So for 2 and 4 inclusive, if you go up here, between, click on between, and now you have between inclusive. And StatCrunch will do only inclusive. So if it's exclusive, you have to kind of be creative with that one. And there you go. 2 and 4, compute, and look at between 2 and 4, 2, 3, 4. These are now in color. That probability is now 0.71. Well, rounded to the nearest 10,000 is 0.72, right? Because of the 9, 9, and the 5, right? So it's 0.72 rounded to the nearest 10,000ths. And that's how you do this. And this is the shape of the binomial distribution. Okay, so let me go back to my notebook now, and we'll finish this portion of the exercise. So for the first part, we found probability of y equals 3 to be 0.2787. We did that ourselves and confirmed it with StatCrunch. Now, probability of at least 3 greater or equal 3, that turned out to be 0.6864, means almost 70%. And probability of at most 3 turned out to be 0.72. Okay, and there you go. See how much easier it is using StatCrunch. Now, so that answers parts A. The answer for part B, let me move this other one down below. Okay, in part B, we want to know the probability between 2 and 4. So that's going to be y between 2 and 4 inclusive. Inclusive. That number, we found it again from StatCrunch, right? That number turned out to be, what, 0.72 once we rounded it. And 0, 0 means that number is rounded. Of course, if you don't put 0, 0, no one's going to fault you on that one. And there we have it. Part B is done also. Now, in part C, find and interpret the mean, and in part D, the standard deviation. Now, for those, we don't need StatCrunch, right? And in fact, StatCrunch doesn't give it to us. So in part C, the mean of the random variable y is going to be NP. That's all. It's really easy. Like, for example, the 40% probability of success, well, in a group of 100, you would expect 100 times 40%, or 40 of them, to, on average, have that condition or attribute. The derivation of this formula, we leave it alone. We're not going to derive this formula, NP. So n in this case is 8, probability of success 0.4, and that number is 3.2. So 3.2 accidents, right, involving intoxicated person. These are fatalities, right? These are fatal accidents, traffic fatalities due to intoxicated or alcohol impaired. In 8 of those kinds of accidents, we expect 3.2 of them be due to those kind of people, intoxicated and blah blah. Now again, remember, we cannot have 3.2 fatalities, right? 3.2. So how do we get around it? This is 3.2 in 8, so we can call that 32 in 80 accidents, fatality accidents, that is, right? Fatality accidents are due to intoxicated person, okay, or alcoholic impaired person. 32 and 80, that's how you get around the decimal. Well, we don't round it, we'll keep it like that. But informally, between you and I would say in a group of 8 or in 8 fatality accidents, about 3 of them, because it's closer to 3, so we could round it that way also. Standard deviation of random variable y is going to be square root of np 1 minus p. And in this case, that is the square root of n is 8, p is 0.4, and 1 minus that is 0.6. And now we can use our calculators, right? We want to find the square root of 0.6, and I found it to be 1.39. 1.39. Or if you think of that as 1.4 rounded. So in 8 accidents, I would expect about 3, give or take 1. That's how I interpret that. Okay, and of course we can now figure out, like we can say, well, so many percentage are within this range, so on and so forth. Also, we can also do that. Okay, and I believe that's all that is. And we did interpret the mean as they expected us to. So there, we are done with that exercise. Okay, let's take a look at another one now, another exercise, and this one it's slightly different. It has a little bit more, and something that you actually do in your homework also. So let's take a look at this one. In this exercise, an article titled "You're Eating That?" published in the New York Times discussed consumer perception of food safety. The article cited research by the Food Marketing Institute, which indicates that 66% of consumers in the U.S. are confident that the food they buy is safe. The food they buy is safe, 66%. So there you go. That's probability of success, 0.66. A success is if somebody believes in that. Somebody is confident that the food they buy is safe. Suppose that 6 consumers in the U.S. are randomly sampled. 6, that's not many. That's probably just people in your household, right? Just near and dear to you. So you're talking about the U.S. population based on just your family. That's massive undertaking, isn't it? Risque. Suppose the 6 consumers in the U.S. are randomly sampled and asked whether they are confident that the food they buy is safe. Okay. Determine the probability that the number answering in the affirmative is, that means yes, is part A, exactly 2. So we're just going to use X on this one since it doesn't say Y. Probability of X is 2. Now some actually write it this way too, just probability of 2. I'm cool with that. That's fine. That's chill. Okay, so probability of exactly 2. Again, just to give you the formula, if you were to do this by hand, so this is, remember, we have a binomial, n is 6, p is 0.66. So that's going to be 6 choose 2, 0.66 to the second power, 0.34 to the 4th power. So if you want to do that on your calculator, more power to you. I'm going to use a StatCrunch. In part A. In part B, probability of exactly 4. X equals 4 is. And in part C, probability of at least 2. X greater than or equal to 2 is. Okay. And in part D, the question is asking us to determine the probability distribution of the number of consumers who are confident in a group of 6. So we actually want in part E, we want something of this type. This is probability of X equal little x. And this is what we want. So X is 0, 1, 2, 3, 4, 5, 6. No success means none of the 6 people are confident the food we eat is safe. or 1 believes it is, 2 believes, 3, 4, 5, or all 6 of them believe, yeah, the food we eat is safe. And there you go. We want to figure out the probability distribution. Now, in part F, what is the exact distribution called? Now, here, because, let's see, these are randomly sampled. Okay. The only thing I can assume here is that assuming sampling is done. Let me just say, assuming sampling is without replacement. Is without replacement. That means you choose one person. You're not going to put him back in the population. Replacement. What is the exact distribution called? The distribution is hypergeometric. And again, don't worry about it. And since he asked for it, I'm answering it. Okay. We don't cover hypergeometric distribution. But anyhow, going forward, we're not going to make that assumption. We're going to assume sampling is actually with replacement, so we don't have to do a hypergeometric distribution. It's more complicated than binomial. Okay, I need to go to StatCrunch, so let's go to StatCrunch and do this. Okay, so I'm back in StatCrunch once again. So let's take a look at now how are we going to do this. I'm going to go again to Stat, Calculators. We're going to go to Binomial and forget the default. Remember our parameters are 6 and 0.66. So n is 6 number of trials. Probability of success was 0.66. Now let's begin with part A, probability of exactly 2. Probability of exactly 2 is 0.0873. Okay, 0.0873. Probability of exactly 4, you just change that to a 4 and compute 0.3290. And in part C, probability of at least 2, that would be greater than or equal to 2, and that's 0.9805. And if the question said, for example, what is probability that more than 3 of the 6 believe our food is safe, more than 3, you just go greater than without the equal sign and 3. See, more than 3. You just got to make sure you translate those probability questions correctly into an inequality. If it said between 2 and 5 inclusive, I'm just making these up. Between 2 and 5 inclusive, it would be that. What if it's between 2 and 5 exclusive? Well, between 2 and 5 exclusive means what? It means 3 or 4, right? Because we don't include 2 and 5. So now we want between 3 and 4. Inclusive now. So you turn that exclusive between 2 and 5 into an inclusive between 3 and 4, and there you go. Notice only 3 and 4 are now selected. Okay, now part of the question also asks to write the probability distribution. So I'm going to go up here, standard. So to actually draw the probability distribution or to arrive at it, we need to know probability of 0, 1, 2, 3, 4, 5, 6. I've already done probability of 2 and 4 for parts A, B. So probability of 0 is going to be 0.0015. Probability of 1, see, you just change it in here, 0.018. Probability of 2, 0.873. Probability of 3, 2, we've already done that one. That's okay. Probability of 3 is 226, rounded to the nearest 10,000. probability of 4, I just did that one earlier. Not going to let that one slip by. That was 32.9. That was for part B of the exercise. Probability of, but if you want to say no big deal, there you go. That's 4. Probability of 5 is 0.2555 rounded, 0.2555 rounded. Probability of 6 successes, all 6 believe that our food is safe, is 0.827. Not even 10%. Probability that all 6 people believe our food is safe. And there you go, 0.827. Now we can go back to my note and actually answer this exercise now. Okay, so here we are. Now I can actually copy the numbers that I had earlier in here. So we found probability of 2 to be 0.873. So this answer is 0.873. Probability of 4 turned out to be 32.9. And probability of at least 2, pretty high probability, 98.05. And in part D was determine the distribution of number of, actually this is part D. I got my D's and E's mixed up, sorry. So this is part D, the probability distribution, and those numbers again. Earlier in StatCrunch I did, and I got 0015, 0180, and 0.0873, 0.2260, 0.3290, 0.2555, and finally 0.0827. So this is how you complete your probability distribution table. Again, on your homework, actually in your homework, you're going to be doing the same thing, and maybe even on exam question will ask you to actually complete a probability distribution table, and that's how you do this. And then just checking, making sure the last digits, these add to 0, so that means my sum of probabilities will be 1, and they do. 5 and 5, 10, that's 0s, 3 and 7, 10, 0, yeah. And this is what I was checking for. Some of these probabilities should be 1, and because I rounded it, I just want to make sure that they look right. Okay, and that's the answer to part D. In part E, strictly speaking, why is the probability distribution you obtained in part D only approximately correct? What is the exact distribution? Actually, parts E and F are all in here. So the reason it's only approximately correct, all these numbers are approximate, is because sampling is without replacement. So that would be, this would be the answer to part D. There, that's part D. And in part E, distribution's name is going to be hypergeometric. So, sorry guys, sorry, I'm not even looking. That's E and F. There you go. Okay, now that looks better. And there you have it. So this is what we want to show. Now, one other thing I just want to show you, and we are done in this with this lecture, and in fact we're done with this chapter, in fact, because binomial distribution is the last thing we wanted to cover. So let me go back to StatCrunch. I was going to show you this binomial distribution. Let me just make up a couple of those. Actually, I can go to Applets distribution demo, and we're going to look at binomial. I just want to show you the general shape of the binomial distribution right in here. So here, here's a binomial distribution where a number of trials, let's make them 20. There are 20 trials, and probability of success is 0.5 right in here. That probability is 0.5. Notice how the distribution is symmetric, isn't it? It's symmetric shape. Now, if I keep probability of success at 0.5 as simply move the slide ruler to the right, that is increase the number of trials, you're going to see that we're going to maintain that symmetric shape. Right now with 20 trials, notice the middle is 10, the center is at 10, and everything's symmetric on either side of 10. Your most likely outcome is 10. And if you do NP, that's 20 times 0.5, you get 10. So your expected value, what you would expect to see, the average is also 10. I'm going to turn that to 30. Notice as I move across all the way from 10 to 60, the shape maintains its symmetry. But look at how the probabilities, of course, change. And at 60, 30 is the center of the distribution. Look at that nice symmetric shape. Hardly any probabilities on either side of the tail. So if P is near 0.5, the distribution will be symmetric. Now, I'm going to keep number of trials at, let's say, 30. And I'm going to change the probability of success. I'm going to make it lower. As it goes lower, probability of success low means in 30 trials, I would expect fewer successes. So I would expect to see this bulge that you see move to the left somewhat here. It's going to be bulky here, right? And there you go. You see that? Exactly as we anticipated. So as probability of success decreases, the distribution becomes more asymmetric. In this case, probability of success low, you expect larger, well, not larger x, but more of the fewer successes, means greater frequency of 0, 1, 2, 3, 4, 5, like that. And as that probability increases, look at that, looks like a tsunami moving through. We expect this to be skewed in the other direction. Okay, and that's what happens when now probability of success is 0.9. So in 30 trials, look at that, we have really high probability of successes. So we expect more successes. Remember, x is a number of successes. So we could even get 30, all 30, if probability of success is 0.9. Definitely 27, 26, 28 are doable, right? Those are definitely possible. And of course it remains the same. And if I change the number of trials to 60, so probability high again of success, you expect a large number of successes. As I lower the probability at 0.5, you get perfect symmetry here, right, at 0.5. Then the tsunami moves to the other side, and there you go. So you can go right and left, and there you go, the distribution's dancing for you. Okay, and there you have it. So I just want to do that distribution demo, and with that we are done with this section. We just want to talk about the binomial probability distribution, and we just did. So we're done with this section, and in fact we're done with chapter 5.